information together. So we have a few learning objectives for this video. We want to be able to describe subatomic particles, describe the difference between those subatomic particles for isotopes, be able to determine the number of protons, neutrons, and electrons in a specific isotope, and as well being able to relate the average atomic mass to the relative abundance and the masses of specific isotopes. So that's our focus for this video and being able to identify those things. So first here, we just have an overview of subatomic particles. We have a relationship between mass, charge, and then how we symbolize that when we're talking about these. So we've already discussed the discovery of these protons, neutrons, and electrons, the subatomic particles. But here what we're doing is we're looking at, well, what are their actual charges and symbols? So to simplify things, what we usually do is we just say, for charges, we just call an electron -1, a proton +1. And what that really means is that this is actually -1 times 1.6 times 10 to the -6 coulombs. So it's a really small charge, but we want to make sure that we know that -1 and +1 corresponds back to that specific charge. Now, as we're doing this, we also want to make sure we know the relative masses of these, right? So a proton and a neutron have similar masses, right? You notice they're not the same, but they're similar. Whereas our electron mass is really, really, really small, right? It's 4 powers of 10, 4 orders of magnitude smaller than our protons and neutrons. So it's important to make sure we note that, especially when we start talking about isotope masses. Now, as we think about where these are located, right, we have our nucleus, and this is dealing with the idea of a nuclear model of an atom. We would have our protons and our neutrons in there, and then around here, in what we'll call our electron cloud, we would have our electrons, right? And our electrons occupy the vast majority of space of an atom, even though they are the smallest mass, right? And all the mass is concentrated in the central part, or the nucleus of an atom. And we'll talk about different modes of how we think about where electrons are, right? We'll talk about a Bohr model of an atom, we'll talk about the quantum mechanical model of an atom, and how those things relate to where those electrons occupy, energies they have, and different things like that. So now that we have this idea of different subatomic particles, we want to look at, well, how does that apply to a specific isotope, right? And so we have different isotopes, and when we're thinking about different isotopes, we need to know what an isotope is and how we identify them. So an isotope is an atom of the same element, so that's real important to note. It's an atom of the same element, but with different atomic masses. Now, what causes them to have different atomic masses? Right, not a different number of electrons, right? Because we mentioned electrons are so much smaller in mass than protons and neutrons, but it's dealing with a different number of neutrons. Now, they must have the same number of protons, because the number of protons is what determines the element of that atom. So if I have two things that have different number of protons, they are different elements. They're different atoms of different elements. Whereas if they have different masses, but the same number of protons, what causes those different masses is a different number of neutrons. Now, in order for us to be able to describe that, we need to be able to know how many neutrons and protons we have and electrons. And we do that by writing out in 2 different possible forms as we're looking at isotope symbols. So the first one is where we just have our element symbol. So maybe something that we would be dealing with here would be something like iron. So iron would be an element that we'd find in the periodic table. And then our Z here is the atomic number, okay? And that atomic number we can just find by looking at the periodic table, and every atom has a specific atomic number. So if we went to the periodic table, we would find iron is atomic number 26. And what that means is that it has 26 protons, and it has 26 electrons as a neutral atom. We also have A, which is the atomic mass number, and this is the number of protons and neutrons. So this is what would differ between different isotopes. So let's say, for example, we had isotope 56 for iron, and that would tell us how many electrons and neutrons and protons we would have. We can also write this out as where X is the element name or the atomic symbol, and then in front of that, or after that, excuse me, we would write the isotope number, and that tells us its mass. So here we could say, for example, this would be iron 56, or we could write it as like write out the name and iron 56. Those are two other ways that we can illustrate the atomic mass numbers as well as the identity of the element. And we notice here is this doesn't tell us specifically the atomic number. And that's because if we know the identity of the element, in this case iron, we don't need to know the atomic number, right? It's already provided for us. We could go to the periodic table and we know that our atomic number is 26. Okay, those two ways we can illustrate our atomic numbers here. Now when we're doing this, what we also want to be able to do is we need to be able to look at these different isotopes and identify the number of protons, neutrons, and electrons as we're doing this. And in order for us to do that, we're going to look at some examples here. Okay, so here we have an example. We want to find out the number of protons, neutrons, and electrons in a single atom of chlorine 36. Now as we're doing this here, we know that it's chlorine. So I'm going to go to the periodic table, and for chlorine, we know that it's atomic number 17. All right, we can go to the periodic table and we see that symbolized on the atomic numbers. Then from there, that tells me that I'm going to have 17 protons, and because this is a neutral atom, we don't have an excess of protons or excess of electrons relative to each other. We also have 17 electrons. So if we have equal number of protons and electrons, it's a neutral atom. Our charge is 0. Then for us to find the number of neutrons, we know that our atomic number, mass number, is 36. So we have our atomic mass number of 36. So we're going to take the total mass, which is contributed by our protons and neutrons, and we're going to subtract how many protons we have. And that's going to lead us with 19 neutrons that contribute to our mass. So we were able to identify the number of protons, neutrons, and electrons in this specific atom of an isotope of chlorine. Now we want to do the same thing for an isotope of chlorine 36, but with a -1 charge. And we'll see what does that mean for us. Again, it's chlorine, our atomic number 17, which tells us I have 17 protons. We can go ahead and identify, we still have an atomic mass number of 36. We subtract from that 17, and we get 19 neutrons again, because this is the same isotope mass. Now we want to figure out the number of electrons. Well, for us to figure out the number of electrons, what we realize here is that we have a -1 charge. And what that means is I have one more electron than protons. And that's because we have that -1 charge on our chlorine atom. So that means I'm going to have, I add one more to that 17, I have 18 electrons, which leads us with an overall charge of -1, because we have one more negative charge than positive charges here with our chlorine atom. So now that we've kind of worked through some practice application here, what I'd like for you to do is pause and practice this. So pause the video and write the isotope symbol for a neutral atom that has 26 protons and 30 neutrons. Well, now that you had a chance to practice this and you pause it, let's go ahead and see how we thought through this. So we know that we have 26 protons, which means we know that that is our atomic number. Well, then I go and I trace myself back to the periodic table, and I find that atomic number corresponds to iron. So now I know it's iron. And so if I want to write the isotope symbol, it's going to be iron. 26 is our atomic number, but we need to know our atomic mass number. And to find our atomic mass number, we're going to take the number of protons, which was 26, and to that, we're going to add 30 neutrons, right? That's our total mass, and that would give us 56. And so this would be isotope 56 of iron. We could also write it this way if we want to show the mass, or we could write it out all the way and say it's iron 56. So those are the ways we can illustrate our isotopes. But now as we're looking at our isotopes, we want to think, why is it important that we know that there are different isotopes, and specifically, what those isotopes are? Well, there's not every possible combination of neutrons and protons. Only some isotopes are stable. And by stable, we mean we'd actually observe them naturally. Well, because of that, when we're looking at these, what we need to realize is, well, how do we correspond that back to the masses that we know and we measure for a large sample of atoms, not just a single isotope and a single atom of isotopes? And for us to do that, we want to look at this idea of what is the average? If I have all these different isotopes, how do I average them out when we're looking at a bunch of atoms? We don't just have one or two atoms, we have 10 billion of them, or 10 times 10 to the, or 1 times 10 to the 20th atoms. We have a ton of atoms. How am I going to get to an average of these? Well, for us to do this, what we want to do is we want to make sure we have some standard we compare these against. And since they're such small masses, we're not going to compare them against maybe a kilogram or a gram. What we do is we compare them against what we call an atomic mass number, or an atomic mass unit. That atomic mass unit is correspond to a specific element and one specific isotope of that element. And so what we'll notice here is that we have carbon-12. Carbon-12 is a very, very abundant isotope of carbon. It's 99.9 something percent of the isotope of the carbon atoms are carbon-12. So the vast majority of them are carbon-12. In addition to that, carbon is a very, 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 very prevalent atom in our world, right? It makes up all the building blocks of nature and living organisms and everything, right? So it's so prevalent. And its carbon-12 isotope is very prevalent. Because of those two things, what happened is that the people that designed this specific mass unit defined it as being 1/12 the mass of carbon-12. So we could say here the mass of carbon-12 is exactly 12.00000000000 AMU. And that is because this mass number has been determined based upon carbon-12. And all the other masses that we record are relative to the carbon-12 mass. Okay? So we are able to identify that. But now, if we look at this, we realize not every element, every atom of carbon is carbon-12. Because if we go to a periodic table, we see that the mass listed for carbon is actually 12.011 AMU. So that's the mass that we would see present on our carbon element here in the periodic table. We notice that this is not a whole number. This is a fraction of a number slightly greater than 12. Now, where did this come from? Every single mass that's present on the periodic table is an average, and what we call specifically a weighted average of all the naturally occurring isotopes of that element. So basically any isotope that is stable, so that will be naturally occurring among the different isotopes. Now, how do we calculate that? What does that correspond to? This is an weighted average, not just an average. An average would be isotope 1, 2, and 3. We add them together and divide by 3. This is a weighted average, and that weighted average accounts for the abundance as well as the mass of a specific isotope. So what we see here is that our average atomic mass is equal to the sum of the fraction of one isotope times its mass, plus the fraction of a second isotope times its mass, plus the fraction of our third isotope times its mass, plus however many isotopes are naturally present. Now, what do we mean by fraction? Our fraction here is some number between 0 and 1. And what it corresponds as the decimal form of the percent abundance of that specific element. Okay, so it's going to be, if something is 52.5% in its abundance, that would mean its fraction is going to be divided by 100.525. And that's the fraction of all the isotopes present would be that amount for that specific element. And then we multiply it by the mass and say that's the contribution that that isotope gives to the mass. And we do that for all of the different elements. And what we'll find is that that mass is close to all the different isotope masses. Now that we have this kind of general idea present, let's go ahead and work through an example together and how we apply this. So here what we have is an element has two naturally occurring isotopes. Isotope 1 has a mass of 120.9038 and a relative abundance of 57.41. So let's go ahead and write that data down. Isotope 1 has a mass of 120.9038. And we'll notice is that we can write AMU or I can write U. We can say those two interchangeably. That's just a shorthand for atomic mass units. We can write U. And then we can say its percent abundance is 57.41%. What we can also say here is that our fraction for isotope 1 is 0.5741. Okay, we would divide that by 100. Then we also know for isotope 2, we have a mass for isotope 2 here of 122.9042 AMU or U. And its percent abundance is not listed. However, what we do know, there's only two of these. So if one of them occupies 57.41% of all the elemental atoms, then we can take 100% and subtract from that whatever is for isotope 1. Now the reason why we can do this is because there's only two naturally occurring isotopes. There's not more than two. And so that would give us an abundance for this specific isotope that we'd be looking at here of 42.59%, which would lead us to a fraction of 0.4259. So now we have that information there. We're just writing down the information that we know so far. From that information, we want to calculate the atomic mass of the element, and then from there, identify what that element is. So let's go ahead and work through this together. Let's explicitly write out our equation that we'd have here. So we know our average atomic mass is going to be equal to the fraction for isotope 1, mass for isotope 1, and that's because that's our first isotope. The fraction for isotope 2, mass for isotope 2. I only include 2 here because we know there's only 2 naturally occurring isotopes. Let's go ahead and fill in the information that we know. So our average atomic mass is going to be equal to our fraction here, which is 0.5741, times our mass, 120.9038 atomic mass units, plus our isotope 2.4259 times its mass, 122.9042 AMU. So now what we normally do is just take that, throw it in a calculator, and go from there. But what we want to do is pay attention to our significant digits and how we do this calculation. Okay, this is a good way for us to process through how we track the precision of a measurement, which is signified in our significant digits. So if I go ahead and plug in this first portion of our equation here into a calculator, I get 69.4109 AMU. Now what I want to do here is I want to pay attention to the fact that I just multiplied those, and the way that I track multiplication and division, significant digits, is different than addition and subtraction. I'm going to add this to the other number. So what I need to do here is I need to track where my significant digit would be. There's 2 ways of doing this. We can either round and then add them, or what I realize here is I got 1, 2, 3, 4 significant digits, 1, 2, 3, 4, 5, 6, 7 significant digits. So I take the one that's least precise, the one with the least number of significant digits, and that's how many I'm going to have in my answer after I multiply them. Well, what I'm going to do instead of rounding here is I'm just going to put a line underneath the number I would have rounded. And that helps me track that that number only has 4 significant digits, 2 digits past the decimal place. And then I can do the same thing for our next number here. We get 53.3449. That comes out of our calculator. And again, we look here, we got 1, 2, 3, 4 significant digits, 1, 2, 3, 4, 5, 6, 7 for our mass. And so then this is going to have 4 significant digits total that we would see here. So now I've tracked those. I didn't necessarily round, but I tracked them. And so now what I can do is I can go ahead and add them together, and I'm going to get 121.7557 after I plug it into my calculator. But again, I need to make sure I track the number of significant digits here. When we add and subtract, we take the number, the least precise number is the one that has the least number of digits past the decimal place. So this has 1, 2. This one has 1, 2. So my number is going to have 2 digits past the decimal place. That's where I'm going to round. And that's because when we add numbers together, I don't know, like we can't trust that 0, we can't trust this 4 to be significant because of the original numbers we used to calculate it. And so this would become 121.76 AMU or U, atomic mass in units, for our mass here. So now that we've calculated that mass, we can go to the periodic table, and we go to the periodic table and we say, okay, what is that specific mass that we would have? And I go to my periodic table and I find that that is antimony, Sb, because its mass is closest to that specific atomic mass that we would have here, and that's what we would identify for our atomic mass. So hopefully this helps us relate weighted to average masses and weighted average atomic mass and how it relates to the percent abundance and the mass of each isotope. Now that we've worked through one on our own together, what I'd like for you to do is now pause and practice on your own. Okay, so I'm going to read this, and then once you pause and try and do this one on your own. Bromine has 2 naturally occurring isotopes, bromine 79, bromine 81, and an average atomic mass of 79.904. That's our average for all those 2 isotopes. The mass of bromine 81 is 80.9163. The natural abundance of that isotope is 49.31. From this information, calculate the natural abundance of isotope 79 and the mass of isotope 79. Why don't you go ahead and pause the video and do this one on your own. Well, now that we hopefully had a chance to practice this, why don't we go ahead and work through this one real quick together. So again, we know that our average is equal to the fraction of isotope 79, mass of isotope 79, fraction of isotope 81, mass of isotope 81. Only 2 isotopes here. So we plug in the information we know, 79.904 AMU is our average. We found the percent abundance for each of these, and that's because we know there's only 2 isotopes. I could subtract it from 100 for isotope 79 to find 50.69% of the isotope, the atoms are isotope 79. And then we don't know what our mass is. And we realize here, we know the average, we know the fraction of 79, we know the fraction of 81, and we know the mass of 81. So it seems here there's only one unknown, and that's the mass of isotope 79. So let's go ahead and plug in the information we have and then finish our calculation. So we have 0.5069 mass of 79 plus 0.4931, 80.9163 for our mass. So we go ahead and we get 79.904, 0.5069 mass of 79. We multiply those 2 numbers together, we get 39.8999. And again, we want to make sure we track our significant digits here, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So this would be the number we would round. We're not necessarily, we don't have to do that right now, but we could. We just want to make sure we track that. Then we go ahead and subtract over our 39.8999, and we're going to get 40.0042 equals 0.5069 mass of 79. And we look here and we see this has 2 digits past the decimal place. This has 3. So the number that I would have rounded at would be our 2 digits past the decimal place, right? We're now subtracting here. And so we treat the number of digits past the decimal place. And then finally I'm going to divide by 0.5069. And we get a mass of isotope 79. We have 4 significant digits for our percentage or our fraction. And so that would become 78.92 AMU, or U would be the mass of isotope 79. So hopefully this gives us some good exposure to average atomic mass, how that relates